Lighthouse Scientific Education presents a lecture in the Stoichiometry series. The topic, Mole Ratio, an Introduction to Stoichiometry. Material in this lecture relies on an understanding of the previous lectures, balancing chemical equations, the mole as a quantity, and molecular weight and conversions. A very legitimate question to open with is, what exactly is stoichiometry? Our lecture begins by addressing that very question. An overview of what to expect with the topic of stoichiometry is then offered. To give some real-world context to this initially complicated subject, we equate the balanced chemical equation with a recipe for making cookies. It works surprisingly well. More specifically, we look at using the ratio of ingredients in the cookie recipe as a way to move from amount information about one ingredient to amount information about another ingredient, which is basically what the mole ratio does in a chemistry context. The mole ratio is further developed as the central component of the process of solving stoichiometry problems. A few example problems are given to support that understanding. So what does this unusual term stoichiometry really mean? It is a Greek term that translates somewhat as measure of elements. Its chemistry definition is the calculation of relative quantities of reactants and products in a chemical reaction. The balanced chemical equation is the necessary starting spot for determining relative quantities. The balanced chemical equation can be used to relate the amount of reactant to another reactant, product to another product, a reactant to a product, or a product to a reactant. Essentially, stoichiometry takes amount information about one substance in the balanced chemical equation and converts it into amount information about a different substance in the reaction. Stoichiometry involves the integration of several chemistry-related skills. Above all, stoichiometry requires a capacity to balance chemical equations. The student needs to be able to determine molar weights or molar masses. It's also necessary to be able to convert between weight and moles, and to convert between molarity and moles. These last two skills are developed in the mole series of lectures. And then there is the ability to determine mole ratios. This is the only new skill needed in stoichiometry. It can't be emphasized enough that weakness in any of these skills will be drawn out when addressing stoichiometry problems. Have a good base before proceeding into problem solving. To understand the mole ratio, we return to the definition of stoichiometry. Stoichiometry uses the coefficients of the reactants and products in the balanced chemical equation to determine the relative quantities. This equation with numbers and letters is just a stand-in for balanced chemical equations in general. Remember, coefficients are the count of the substance, not the weight, and is done by moles, so coefficients give the numerical relationship between all species in the reaction. The stand-in equation is read 1 mole of compound A plus 2 moles of compound B form 3 moles of compound C and 4 moles of compound D. Importantly, the coefficients in the balanced chemical equation will never change. They are just the numerical relationship between the compounds in the reaction and are not to be taken as specific amounts. Using this stand-in for a balanced chemical equation, an example stoichiometry question would be, given 2.2 moles of chemical A with sufficient B, how many moles of chemical C can be produced? Note that in this question, the value of 2.2 moles of A does not correspond to the 1 mole coefficient in the balanced equation. A stoichiometry problem can use any value for one of the compounds. It uses the balanced chemical equation with its set values as a way to get relative quantities. The coefficients of the balanced equation are not the relative quantities the problem seeks, but rather they are the means to get that value. It will be of utmost importance that as we advance in our study of stoichiometry, that we recognize when and where we use the amount values in the question or problem and the amount values in the balanced chemical equation. A second very similar example asks the question in a more real-world term. Given 10.0 grams of chemical A, again with sufficient chemical B, how many grams of chemical C can be produced? The difference between these two examples is the difference between a solution with a single calculation and a solution with 3 separate calculations. It is the difference between this lecture and the next lecture. Let's look at this difference in a little more depth and patiently build up the process of stoichiometry problem solving. Stoichiometry problems are initially difficult to get a handle on because many are solved in 3 parts. The refrain that will be used repeatedly in the study of stoichiometry will be get into moles, mole ratio, it is the center of the solution, and get out of moles. The good news is that the get into and get out of moles are skills already covered in previous lectures. Most students will be familiar with these calculations. The bad news is that combining 3 separate parts into one solution is inherently complex. It takes time for the complex problem solving to start to feel more comfortable. Struggle and confusion are normal at the start of the study of stoichiometry. The best advice at this point is to take your time and focus on each part separately. As such, this lecture is only concerned with the mole ratio. The mole ratio is not a wholly new concept. It is really just a conversion factor based on the coefficients of the balanced chemical equation. The balanced equation and the mole ratio can be understood using a more familiar ratio and relationship. It is the recipe, as one might find in a cookbook. While it might not seem so at the beginning, the balanced chemical equation is like a recipe in a cookbook. Consider a basic cookie recipe. This one makes 1 batch of cookies. It has 2 types of information. One is the ingredients needed to make cookies, and the other is the amount of each ingredient. The balanced chemical equation has 2 types of information. One is the chemicals in the reaction, and the second is the amount in moles of each chemical. Here we take the recipe and put it into a format similar to the chemical equation. The ingredients that go into making the cookies are the reactants, and the final product is the batch of cookies. The amount of reactants and products are included. We see that both the chemical reaction and the recipe in reaction format give relative quantities of their components. Since they are laid out in a similar format, using a recipe to get relative quantities is similar to stoichiometry. That is because amount information about one ingredient can be used to get amount information about another ingredient. We can explore that, starting with how ingredients can be viewed in ratios. And as we've seen before, ratios can be used as conversion factors. For example, it takes 3 cups of flour for every 1 batch of cookies. It also takes 3 eggs to make 1 batch of cookies. From this recipe, a ratio of flour to eggs can be made. Many different recipes use flour and eggs. This one uses them in this ratio. That ratio can also be flipped over, and is still a valid ratio. Now consider the 3 cups of flour and its relationship to the sugar in the recipe. A ratio of 3 cups of flour to 2 cups of sugar could be made, as can the reciprocal. Again, the quantity matters because in different recipes, flour and sugar can come in different ratios. For completion's sake, we can add how the flour relates to the butter in the recipe. It is in a 3 cup to 1 cup ratio, or it can be given in a 1 cup butter to 3 cup flour ratio. This series of ratios relates the proportion of every ingredient in the recipe to flour. But what about the product, 1 batch of cookies? Can the flour in the recipe be related to the 1 batch of cookies? Yes, it can. It can be written as 1 batch of cookies over 3 cups of flour, or 3 cups of flour over 1 batch of cookies. What can be gathered is that a ratio can be made with any component in the recipe with any other component. That's all fine and well, but how are these related to stoichiometry? An example or two should help clarify their value to our study. Here's a problem that gives information about one component in the recipe and asks for information about another component. Say that we have 2.3 cups of butter, and we want to know how many batches of cookies can be made. Initially, we will assume that we have sufficient quantities of the other ingredients, so that we can just focus on the butter and the batch of the cookies. An important factor this question points out is that quantities of the components can be given at any value and are not limited to the values in the recipe. Butter need not be given at 1 cup. Like the balanced chemical equation, the recipe simply gives a numerical relationship between the components. This is a conversion problem. We need to convert information about 2.3 cups of butter into information about batches of cookies. In the terminology of conversions, the butter is the current or given units, and the batch of cookies is the desired or wanted units. To complete this conversion, a conversion factor with current units in the denominator is needed. To get our conversion factor, we go to the recipe and find the butter. The quantity is 1 cup of butter. We also need the desired units, which is the batch of cookies. Its quantity is 1 batch. Written as a ratio, it is 1 batch of cookies over 1 cup of butter. The butter is in the denominator so that units of butter cancel out, leaving some simple math and a final answer of 2.3 batches of cookies. Information about batches of cookies from information about amount of butter. A second example uses the same recipe. How many cups of sugar are needed if 7 eggs are used, assuming sufficient quantities of the other ingredients? Again, this is a conversion problem, with 7 eggs as the given units and the cups of sugar as the desired units. What is the conversion factor, based on the quantities of the recipe, needed to convert amount information about eggs into amount information about sugar? Looking at the recipe in its equation format, we see that the given units of eggs and the desired units of sugar come in a 2 cup of sugar to 3 egg ratio with egg in the denominator so that the units of eggs cancel out. The math has 7 times 2 divided by 3 for 10.5 cups of sugar. The recipe is the means by which amount information about one component can be used to get amount information about a second component. We are now ready to move back to the balanced equation and repeat this process for reactants and products. Unlike the cookie recipe, reactants and products in the chemical reaction are not given in cups. They are given in moles. But like the recipe, we can generate ratios of one compound to another using the coefficient values in front of the compounds as relative amounts. For instance, with the standing equation, 1 mole of A over 2 moles of B. This is what is meant by the term mole ratio. It is the number of moles of one compound over the number of moles of another compound. The numbers are the coefficients in the balanced chemical equation. Now, compound A and B might also be part of a different chemical reaction and have different coefficients from its balanced equation. This would lead to a different mole ratio. This mole ratio is only valid for this equation. Just like the ratio of sugar to flour in the cookie recipe is only valid for that recipe. Mole ratios with compound A in the numerator can also be made with the other 2 compounds in the reaction, as long as the proper coefficients are included. There is no issue mixing reactants and products in a mole ratio. A mole ratio with compound B in the numerator can be formed with compound A, as well as with compounds C and D, as long as the proper coefficients are included. Compound C can be in the numerator of mole ratios with compound A, B, and D. Not surprising, mole ratios with D are also possible when the correct coefficients are added. This is an exhaustive list of all possible mole ratios given this stand-in equation. Each compound is in the numerator of ratios with all other compounds, and each compound is in the denominator of ratios with all other compounds. The mole ratio is no more complicated than that. Just to solidify our understanding, we could take the balanced chemical equation of this combustion reaction and ask what are all the possible mole ratios. There is no correct order, only that each compound be in the numerator of a ratio with each other compound, and that each compound be in the denominator of a ratio with each other compound. As a reminder, when no numerical value is given in the balanced chemical equation, it is assumed to be a 1. Starting with the first compound, a mole ratio can be generated with 1 mole of C6H12 in the numerator and 9 moles of oxygen in the denominator, and one with 6 moles of CO2, and one with 6 moles of water. 1 mole of C6H12 with each of the other compounds. Moving to mole ratios with the oxygen and its coefficient of 9 in the numerator, there is a mole ratio with 1 mole of C6H12 in the denominator. It's a 9-to-1 ratio. And then there is a mole ratio with 6 moles of CO2 and one with 6 moles of H2O. 9 moles of oxygen in a ratio with all of the other compounds in the reaction. For the carbon dioxide, in the numerator of the mole ratio, there is 6 moles of carbon dioxide for every 1 mole of C6H12. 6 moles of carbon dioxide for every 9 moles of O2, and a 6-to-6 ratio with water. There is no consideration of whether a compound is a reactant or product. Finally, there is the 6 moles of H2O. It forms mole ratios in the same manner as the other 3 compounds. This is a complete list of all possible mole ratios based on the balanced chemical equation. Now that we have a sense of what it takes to generate a mole ratio, it is time to look at using mole ratios to help solve stoichiometry problems. In all of chemistry, no subject is in more want of a procedure than stoichiometry. Provided here will be the basis of solving stoichiometry problems, but is only focused on the central part of the process. In the refrain, get into moles, mole ratio, get out of moles, the central part is the mole ratio. In the next lecture, this procedure will be expanded upon to include the get into moles and the get out of moles part of the solution. Here we focus on the mole ratio and limit the problem and problem solving to amount information already given in moles. The very first thing to do is to write out and balance the chemical equation of the reaction. Since this part of a stoichiometry problem is essentially a conversion problem, the identification of the given or current substance and the wanted or desired substance is needed. Using the language of our general problem-solving procedure, what are the known and unknowns? The problem will provide amount information about one substance, known, and ask for amount information about another substance, unknown. With this information in hand, write out the mole ratio from the balanced equation in the center of the solution equation. Be sure the mole ratio is oriented so that the desired moles are in the numerator and the current moles are in the denominator. Finally, complete the conversion by multiplying the amount of given or current substance by the mole ratio. Remember, this procedure is limited to problems that provide amount of the given substance in moles. Put this value in front of the mole ratio. Be sure to cancel out current units. While this is, in essence, a conversion problem, it is enormously helpful to practice and become comfortable with the mole ratio part of the problem solving before adding in the other two parts of the problem solving process. Let's do some example problems. How many CO2s can be made from 3.3 moles of O2? Does this problem provide amount information about one compound in the reaction and ask for amount information about another compound? It does, and that makes it a stoichiometry problem. The first step in the procedure to solve such problems is to get a balanced chemical equation. Is this equation balanced? Well, there aren't any coefficients, so that probably means no. Since this is not a lecture on balancing equations, which is a skill needed to be mastered before taking on stoichiometry, we will insert the appropriate coefficients. To avoid confusion with the C6H12, a coefficient of 1 will specifically be included. Is this equation balanced now? If we were to sum up the number of each atom type on both sides of the equation, we would see that there are the same number of carbons, oxygens, and hydrogens on the reactant and product sides. It is balanced. Step 2 is to find the known and unknown. This requires a closer reading of the problem. It asks us to find the number of moles, CO2. That is the unknown. Moles of CO2 is the wanted or desired units. The other piece of information from the problem is with the compound oxygen. It is given as 3.3 moles. The 3.3 moles of oxygen is the current unit in this problem and is considered our known. It doesn't matter which order the known and unknown are determined. It only matters they are correctly identified. It's time to find a mole ratio involving the desired and current units. Can we just go to the known and unknown in the previous step and write down that ratio? No, we cannot. The mole ratio is not determined from the amounts given in the problem. It is only found by an examination of the balanced chemical equation. There are no circumstances in which values from the problem are used to get the mole ratio. There are 6 moles of carbon dioxide in the equation. 6 moles of carbon dioxide is the desired units and will be in the numerator of the ratio. The other compound is the current units, the oxygen. There are 9 moles of oxygen according to the balanced equation. 9 moles of oxygen will be in the denominator of a mole ratio. This is a 6:9 ratio, carbon dioxide to oxygen. The second part of this step is to begin the solution equation with the mole ratio in the center. To convert from amount information about oxygen to amount information about carbon dioxide, we take the given units of 3.3 moles of O2 from the known and unknown setup and place it before the mole ratio. Verify that the units moles of O2 cancel out. The math comes out as 2.2 moles of CO2. In this reaction, 3.3 moles of oxygen can produce 2.2 moles of CO2. That is a powerful statement and is why stoichiometry is so central to the study of chemistry. The second mole ratio problem asks how many moles of water are made in a reaction that consumes 5 moles of O2. Is there amount information given about one compound in the reaction and amount information asked for about another compound? That is the definition of a stoichiometry problem. Like all stoichiometry problems, this one begins with the chemical equation. Most of the time the reaction is given. Coming up with an equation is actually very difficult. The reaction is hydrogen gas plus oxygen gas forming water. Is this a balanced equation? Well, there are 2 oxygens on the reactant side and only 1 on the product side, so no, it is not. This is a common equation, and we might remember that it balances something like this. Again, there's a compound that has no coefficient, which is implied to be a 1. Is this equation balanced now? A look at the tally of reactants and products shows there to be equivalent atoms on both sides of the reaction. Proceeding to the known and unknown, we return to the problem. It asks for moles of water. That makes this the unknown and the desired substance. Add that unknown to our setup. What else can we glean from this problem? It does discuss the reactant oxygen and gives a value of 5 moles. This is a known, and it is our current or given substance. The next step is to find a mole ratio from the known and unknown. From the balanced equation, we see the desired units of 2 moles of water and the current units of 1 mole of oxygen. Again, it would be a mistake to put the 5 moles from the problem into the mole ratio. The mole ratio only contains values from the balanced chemical equation. Here's a mole ratio based on the current and desired units. Is this the correct orientation of the mole ratio? No, it is not. The current units of moles oxygen are not in the denominator. But for demonstration purposes, let's see what happens if we use this incorrect orientation. We will start the solution equation with the orientation of the mole ratio in the center of the solution equation and move to the last step in the process. Convert the given units to the wanted units using the mole ratio. What are the given units in this problem? They are the 5 moles of O2. It would be a mistake to place the 1 mole of O2 found in the balanced chemical equation into this conversion. The balanced chemical equation is only used for the mole ratio. Back to the problem. Do units of moles of O2 cancel out with this orientation of the mole ratio? They do not. Moles of O2 are in the numerator of the mole ratio, so they do not cancel. This mole ratio needs to go. Returning to the mole ratio step, here's the correct orientation. And when placed back into the equation, moles of oxygen cancel out, leaving moles of water. It is the canceling of units that catches this type of error. The math is quite easy. 5 times 2 is 10. In this reaction, 5 moles of oxygen can produce as much as 10 moles of water. A final problem has the question, 2.2 moles of chlorine gas require how many moles of sodium to react completely? Does this problem provide amount information about one compound in the reaction and ask for amount information about another compound? It does. So we have a stoichiometry problem. A quick note. That statement in the problem, to react completely, implying that there's enough of the other reactants, will often accompany a stoichiometry problem. In the advanced concept lecture in this series, we look at reactions in which there is not enough of one reactant to completely use up a different reactant. But that's a topic for another time. Here we ask, is this equation balanced? There are 2 chlorines on the reactant side and only 1 on the product, which means that it is not. Fortunately, this equation balances quite easily. We will skip adding an implied 1 coefficient in front of the Cl2. A quick check of the tally shows the equation to indeed be balanced. On to an investigation of the problem to find a known and unknown. It asks for moles of sodium, so this must be our unknown. It is also the desired or wanted units. we see information about chlorine gas, Cl2. It has given amount, so it is our known value. It is our current unit or our current substance. With this information, we set out to find the correct mole ratio. It will have desired moles in the numerator and current moles in the denominator. From the balanced chemical equation, the coefficient of the unknown or desired units of moles of sodium is found to be 2. And how many moles are there of the known or current substance chlorine gas? Yes, it is the implied 1 mole. The mole ratio is 2 moles of sodium over 1 mole of chlorine gas. Again, the 2.2 moles of chlorine in the problem do not come into play in getting a mole ratio. Mole ratios are independent of the problem. They are solely determined from the balanced chemical equation. The orientation is correct because the current units of moles of chlorine are in the denominator. Take the mole ratio to the solution equation so that it can act as a conversion factor in going from current units to desired units. The conversion takes the given value of 2.2 moles of chlorine and multiplies it by the mole ratio. Cancel the moles of chlorine gas to verify the orientation of the mole ratio, and the math is 2.2 times 2. That gives a final answer of 4.4 moles of sodium. It takes at least 4.4 moles of sodium to completely react with 2.2 moles of chlorine in this reaction. The central problem in stoichiometry is a conversion using the mole ratio. Be clear on how and why the mole ratio is used before moving into the other components of the stoichiometry problem, one step at a time. To recap, stoichiometry is a calculation of relative quantities of reactants and products in a chemical reaction. It uses the coefficients of the reactants and products in the balanced chemical equation to determine relative quantities. As such, stoichiometry is a powerful tool in the study of chemistry. We introduced the refrain that will hold stoichiometry problems together: get into moles, mole ratio, get out of moles. In this lecture, we focused on the center part, the mole ratio. It is a fraction or ratio of the appropriate coefficients of reactants and or products from a balanced chemical equation. For instance, using the stand-in equation, 2 moles of B over 3 moles of C is the mole ratio, as is 3 moles of C over 2 moles of B. The mole ratio is a conversion factor that can be used to determine relative quantities of other compounds in a chemical reaction. In this lecture, we used ingredients of a recipe to show how they can be used to make conversions similar to those of the mole ratio. A set of steps was laid out to handle the central part of the stoichiometry problem. It is limited to problems that give the current units in moles. First, write out and balance the chemical equation of the reaction in the problem. That is where the mole ratio will come from. Then identify what the problem gives as the current substance with its units, and the wanted or desired substance, a known and an unknown. From these substances and the balanced equation, write out the mole ratio and place it in the center of the solution equation. The conversion is complete when the amount of given or current moles is multiplied by the mole ratio. Cancel units to verify that the mole ratio is in the correct orientation. And that concludes our lecture. The mole ratio is the center of stoichiometry.